Good morning to all. I am Dr.S.V.Mahesh Kumar, Associate Professor, Department of ECE, Bharat Institute of Higher Education and Research. In the last class, we discussed about embedded system design using microcontrollers. We discussed various microcontroller families used for embedded system design and what are the selection criteria for microcontrollers in embedded system design and what are the IO devices are used, what are the interfacing devices are used, everything we discussed in the previous class. In this class, we are discussing about partitioning, decision, and embedded system design. So let us start the session with the following contents. So what are the contents of this presentation are hardware and software partitioning. So these are the broad categories of a partitioning, hardware and software partitioning. Embedded system means a software, application software is integrated in a hardware. So we are discussing about a hardware and software partitioning as a beginning point. And then we discussed about the duality of software and hardware. A application software is integrated in a hardware, so both are important and design parameters are involved with both hardware and software. So the duality of software and hardware concept is next concept. And then we discussed about the advantages and disadvantages of a hardware solution and a software solution. And then we discussed about various processing steps of implementing a hardware software duality. And then we discussed about the hardware software duality, how it is implemented in a application specific integrated circuits. And then we'll discussed about a system on chip concept. And then we'll discussed about a modern hardware software design flow and co-development design flow, and then general embedded system design cycle, and then incremental hardware software integration. Finally, we conclude this session with future of embedded system design. So these are the references used for this presentation. So first content, that is hardware and software partition. We already discussed about embedded system design as application software is loaded into hardware. So our design architectural design principle also containing two process categories. The first one is software process and the second one is hardware process. So the software process involved with a design of algorithm. You need to solve a particular real-time problem. So you need to write an algorithm to solve the particular issue. We can use a C, C++, any programming language to develop that algorithm. And then hardware architectural design considering about a hardware descripting language. So we need to build up all hardware elements using a hardware description language. After that, we need to integrate a hardware and software. You need to you need to load the program into your hardware. So this is the final step of a embedded system design. So what is the principle of duality of a software and hardware? In an embedded device, hardware and software work together to solve a problem or a algorithm. So a real-time problem is solved with the help of a hardware elements as well as a programming principles. So it is purely depending upon the hardware limitations as well as a software limitation. So a design parameter should be concentrated about the design procedure should be concentrated about a hardware design as well as a software design. And then the decision on how software components and hardware components are partitioned is typically determined by speed and cost. Suppose you are designing a high performance device means we need to provide a high speed. So high speed means the execution time is very less, so the operating frequency should be greater. This is the hardware consideration. And then software point of view, you need to concentrate about the loops, how many loops are used, and then how many library functions are used. So the entire speed is with respect to this loops and as well as a operating frequency of a hardware. If you are designing a high performance device, means the cost will also increases. So we need to concentrate about a optimal programming and a optimized design, and then only we can design a high performance device with a low cost and high speed. So these are the very important basic principles in hardware design as well as in software design. So hardware solution. So hardware solution means you need to build up a hardware elements according to the requirements. Requirements means the solution to solve a real-time, real environment problem. So you need to design what are the parameters are required to solve our real environment application, and according to that application, we need to build a hardware elements with the help of any hardware description language. Here we are using Verilog and VSTL for hardware development. And the other case, we need to develop a software also. So in software, we are using a C or C++. Any real extensions of a C programming is used for a software development. In HDL, a hardware architecture is defined and then compiled to a silicon chip to create the circuit used for a real environment application. This is called as silicon compilation. An IC development process that needed whole teams many years ago. So what is the reason is we have a limited number of library functions, and we have a limited number of modules, pre-requesting modules in the earlier. Now we have enough library functions and a pre-requesting modules, so it will reduce the design time as well as it will increase the efficiency. So these are the advantages and disadvantages of a hardware solution. So greater speed increase can be achieved by a hardware solution. We already discussed about microprocessor and its speed, which is related to a oscillator frequency used, crystal oscillator frequency used. To attain a high frequency of operation, we need to choose a crystal oscillator according to that. Here also we are considering the parameter. For achieving a greater speed, you need to concentrate about a hardware solution only. And a hardware solution requires less processor complexity. And then a hardware solution requires less software design time. What the reason is, we need to solve a issue with the help of hardware, so we need to concentrate less on a software design. So these are the advantages of a hardware solution. Then what are the disadvantages of a hardware solution means? A hardware cost will be increased if you go for a hardware solution. And then additional circuit complexity also one of the limitation of hardware solution. To solve a problem, real environment problem, we need to use a modules, more than one modules. So it will create a circuit complexity. So we need to concentrate about the synchronization between the modules, and then what are the clock frequencies are used, and what is the chip size, chip area, everything we are concentrating. So by adding an extra module, the additional circuit complexity will be created. This is the major limitation of a hardware solution. And then long development cycle and costly design tools are the other limitations of a hardware solution. What is the thing is, we cannot develop a hardware solution within hours or like that. In a software solution, we can easily modify the program, everything. But similar to this software solution, compared with this software solution, a hardware solution is typically a difficult one. So it need a long development cycle, as well as the designing tools are also costly. In a software solution, we are using many open source softwares. So, and then we are using a familiar softwares like C and other things. But in case of a hardware solution, the softwares are a specific only. Specific softwares like HDL and VSDL are used. This specific softwares require a specific training for a programmers, and then the specific software's cost is also high compared with a software tools. So the hardware solution is a costliest one. And then what are the advantages and disadvantages of a software solution? What is the software solution means? There is no additional impact on material cost because we are writing only a program, so there is no additional impact on material cost. Power requirements, we don't add any extra elements, hardware elements, so power requirements is also the same. And then circuit complexity also, it doesn't bother about the circuit complexity because we are writing a coding in a software solution. And bugs can be easily solved in a software solution. With the help of a debugging software, bugs can be easily solved in a software solution. And then design tools are relatively inexpensive. We can use many open sources also. And then what are the disadvantages of a software solution is relative performance versus hardware is inferior. We cannot solve all the problems by a software solution. So a real environment problem means we need to solve it with the help of a hardware also. So it is a relative performance versus hardware is always inferior. And then additional algorithmic requirements forces more processing powers. We are using more loops and other things means it will increase the execution time. If the execution time is increases means it will require a processing power, so it will increase the processing power also. And then larger software development team adds to development cost. We need to develop a more modules and other things. It will increase the team size of a software team, so it will also impact on the development cost. It will also reflected on the development cost. So development cost is ultimately increases if we are using larger software development packages. So this is the implementation example. Your AND gate is implemented. You can see in this AND gate, A and B are the inputs and C is the output. Here A, B and C are a Boolean functions. So we can write A, B and C in terms of ones and zeros, binary values. In a C language, this is a software solution, simple software solution for this AND gate. Boolean A, comma B, comma C, because all the values are Boolean represented as a Boolean algorithm. So A, B and C is declared as Boolean functions, and C is equal to A and B. C output is derived from the input A and B. It is depending upon the input values A and B. It is a simple C language programming. And then a gate level hardware design, it is represented in the right hand side. You can see AND gate is there. So we have a 4 gate levels, 4 gates. Then the first gate A1, B1 is the input and C1 is the output. The second one A2, B2 are the inputs and C2 is the output. The third one A3, B3 are the inputs and C3 is the output. And the fourth one A4 and B4 are the inputs and C4 is the output. So 4 gates are integrated in the chip. So it is a gate level hardware design. We can implement using a hardware language. Verilog language is used here. Here A and B are considered as OS. These inputs are considered as OS and the output is considered as register. Now you can see register C. Here C is equal to output and OS A comma B. So A and B are the inputs and assign C is equal to A and B. The output function C is equal to A and function with B. Finally, we will get the output. And the output is stored in C. The output is displayed through the C. And then hardware software duality implementation. And then the previous part we are concentrating about a simple programming, and we are concentrating about what are the inputs are used, how the inputs are declared, how the output is declared, what is the relationship between input and output, what is the processing related with this input and output. Here we will discuss how it is practically implemented. So we are writing a program, a C language, it's a software solution, we are writing a program. After that we need to convert it as a algorithm. So before convert it as an algorithm, you need to compile it because machines can understand only the machine code. So you need to convert your programming, that is high level language, into a machine code using any compilers. And then finally the application program is loaded into your hardware. Here a hardware design is there. So this programming is converted through a Verilog compiler. After that, it is used to build a hardware modules of the chip. Finally, your application algorithm is loaded into these chips. So hardware software duality is used in application specific integrated circuit ASIC. So a hardware source code compile fabrication instructions for silicon boundary. A software source code such as a C, C++ and compilers to firmware. A firmware is a device where your application software is loaded. Your application software is loaded in a hardware. Our MP3 player is the example for a firmware application. You are loading a program to play the songs. It is loaded in your firmware, and you have a program memory as well as a data memory. In the data memory, we are storing our data, songs and other things. We can access our data, and our program is run through the firmware operation. So the partitioning decisions are purely it is engineering choices. In the case of a MP3 player, the program memory is very less because we are using that program only to play the songs and then change the songs, other thing, and accessing the memory. These are the only functions we are using. So it requires only a less memory. So the program memory is very allocated as very less amount, and then in the case of MP3 player, the data memory is more memory is allocated for data to store a song or playlist, everything. So it is purely engineering choices. So partition is purely engineering choices. And then modern ASICs are dynamically reconfigured. So we can nowadays you can see the firmware can be upgraded. So we can use modern devices can dynamically reconfigured. So it is a major advantage of a modern devices. It's a next level concept, a system on chip. Everything is integrated inside a chip. So what are the using ASIC techniques we are integrating? What are the elements of the system on a chip? I will explain. First, a embedded microprocessor. It's like a heart of the system on a chip. Embedded microprocessor is related to it is responsible for ALU operations as well as control operations, and then commercially available devices. The external interface is also connected to the system to solve a real environment applications, to solve a real environment problems, and then user designed elements also can be connected. Then only the device can be support the external world instructions, the external world operations. So it is important to interface the other devices to the system itself. And then firmware is there, and then firmware environment can be upgraded in the modern devices, and then it can support a analog input and output as well as a digital input and output. In the modern devices have inbuilt ADC and DAC itself, because analog signals, most of the signals, real environment signals are analog signals. For example, our voice signal is a analog signal. So your microprocessor can process only a digital signal. So before processing the signal, we need to convert it into a digital signal with the help of ADC. The ADC can be analog to digital converter, can be used as a on chip or a off chip. Modern devices allowed a on chip ADC as well as a DAC also. What's the use of this DAC here is, suppose you want to hear my voice again, you want to play my sound signal, everything. So this is analog signal, but your system's output is in the digital signal. So you need to convert again as a analog signal with the help of DAC. So ADC and DAC can be integrated within the chip itself to process a real environment sound signals and other signals also. So these things also concentrated during a design of a embedded system. So this is the modern hardware software design flow. You can see this is the iterative process is there. So it's a core design phase. So in a software process, we need to write a C, C++ code. You are writing application program with the help of languages C or C++. After that, your device is not only a software, it is a combination. You have hardware as well as the software. You are loading, you are integrating, you are programming application program inside the chip only. So your program should be compatible with the hardware elements also. So you need to write a subcode to simulate a hardware, and then you need to compile to a object code, and it is integrated in. It is concentrated about also a hardware process, so it is a code design phase, so it's concentrated about a hardware also. You need to write a HDL code to build up the various hardware elements of the chip. After that, you need to write the test vectors for that. After that, you need to compile it, and finally it will integrate it in a chip. What is the final product is, it contains a hardware modules required to solve a particular application, as well as the application program which is required to solve a particular real environment application. So these are the various abstraction layers. So you start with a user interface command, and then RTOS is there, application software driver and physical hardware. Your user commands is finally loaded into a hardware with the help of many layers. So we need to, in the modern devices, we are using RTOS, real-time operating systems we are using. So this is the code development design flow of an embedded system. We already explained about these things. A code design phase concentrated about a hardware part as well as a software part. It's a, you can see here it is a iterative software, and this is respin the ASIC. These are the features of your code development design flow. A final product is integrated in a chip itself. So we can concentrate about some point in during your hardware design as well as a software design. During the software design process, we need to concentrate about what are the loops are used, what are the library functions are used, what are the inputs we are concentrating, what are the time delay, everything we need to concentrate it. And then we need to concentrate about a code, stuff code to stimulate the hardware itself, because you need to access a corresponding hardware according to the programming. If you are getting, for example, you need to generate a timing signals which is related with a hardware part of a timer, and then so you need to access continuously a hardware according to the requirement of your real-time application. So you need to write a stub code to stimulate the hardware itself, and then compare to your object code, and finally it is integrated in the etc. So your co-verification process is concentrated about a generation of vectors and the validation of interfaces. Everything is concentrated, and our system design process concentrated about what are the partitions is required and what is the movement of a partition, other thing, and then what are the simulation parameters. Everything we need to concentrate during a system design process. What is the thing is, the entire thing is iterative and a respin for a hardware. So this is the general embedded system design cycle. What is the thing? Suppose you want to design an embedded product, means first of all we need to get the requirements. Based on the requirements, you need to design overall or design. After that, you need to write a program for that, and then you need to write a program to design a various hardware modules, and we need to test it. After that, we need to integrate it. So these are the various phases of a embedded system design cycle. So first of all, we need to design, that is known as architects and specific. So based upon the requirement, we need to choose the hardware, and then what are the elements are used, what is the specification of that element. Everything you need to decide within this architect process itself. After that, you need to write a software development. So you need to write a application software. You need to develop a application software with the help of any C, C++, any programming language. And then you need to find out what are the errors are in the programming with the help of a debuggers. After that, compilers are used to convert your programming into a machine code, and then RTOS is used to access and user provides a nice user interface for a high performance systems. And then in the hardware development, you need to concentrate about what are the, you need to build up a hardware elements. using emulators, and then circuit emulators are there. After that, you need to test the design parameters before integrated it in a chip. Then after that, after integrating it in a chip, you need to maintenance and you need to provide a further upgradation, or it is known as enhancement. So this is the general embedded system design cycle. So it is followed in most of the high performance device development. So it is a very important phenomena. These parameters are concentrated to develop a high performance device. So what is the necessity? Why we go for a co-verification means? Because respinning an ASIC is a costliest one, because it is ASIC, application specific integrated circuit, is the hardware part. So respinning is always a costliest one. So we need to go for a co-verification process. And fixing a problem in software will reduce the performance. All the software related things also reduce the performance. Unnecessary loops are there, and then unnecessary functions, necessary and time consuming loops are there. Everything will reduce the performance of the systems, because the performance of the system is purely depending upon the execution time required to solve a particular issue. For a real environment systems, it required very less execution time for a coding. So you need to write a optimized coding for that. So fixing a problem in a software will reduce the performance. And then hardware software co-verification focus on validating the correctness of the design across hardware software interface. So you need to validate whether the hardware is whether synchronized with the software, whether the software element can effectively access the various hardware elements, hardware modules, and then any errors are there, everything we need to check up during this co-verification process. Then only we can produce yes accurate and then high performance device, embedded device. So this is the incremental hardware software integration. You can see from the specification, you can know what are the elements are there. After that, you need to allocate what is the program memory, and what is the data memory, what's the amount of program memory is used, and what is the amount of data memory used is purely depending upon application. That is not, after your partition is purely an engineer's choice here. After that, you need in a hardware, you can develop algorithms to design a hardware modules, and then you can develop the algorithms to solve a practical applications using a C or C++, and then you are testing your coding, and then finally you are integrated it, and then you can iterative process of hardware is achieved through ASIC spin, and then the software also iterative process is achieved, and finally we are providing a maintenance and upgrade versions for a practical implementation or practical success of embedded system. So the future of embedded systems. So embedded systems, in the earlier days, we can develop the embedded systems in the board. After that, we can develop it in a chip itself. Now the system is integrated in a chip itself. System on chip is the advanced concept. So it is really purely related with technology used for development, hardware development. 0.35 technology is used. It can accommodate 10 to the power 6 gates, greater than 10 to the power 6 number of gates, and then 0.018 technology can accommodate 4 into 10 to the power 6 number of gates. So we can adapt more number of gates inside the hardware whenever the design technology is advanced. So advanced design technology accommodated more number of transistors, so it can support to design a compact devices, and we can integrate a more hardware modules within the chip itself. So system on chip concept is advanced through this design advancements. So we can develop a highly practical oriented embedded systems we can achieve the efficiency through this chip designing technologies by adding more number of transistors on a chip, by adding more number of hardware modules on the chip. Thank you.